I took the time to read about the maximum modulus principle in several books, but first I want to read a little something out of Nehari, which I think is a way for me to realize why it is not an empty exercise for me to torture myself with this book. I think it's got a lot of good stuff in it that I want to learn, and I'm still on the trip of completing it. Oh, that marker went somewhere. Yeah, okay, well that was where I was going anyways, so that's good. So right here, Nehari says something that I think is profound. Okay, so the theory of analytic functions of a complex variable and the theory of harmonic functions of two real variables are essentially one and the same thing. That's profound in my opinion. So it's possible to avoid the use of complex quantities altogether and to obtain all the results of complex function theory without leaving the field of real analysis. But there's two reasons why that is not done. The first one is the elegance and convenience of manipulating in complex algebra. The second one is that operations with complex quantities are the analytic equivalent of geometric facts. So it's complex thinking is essentially geometric thinking. So that's I really like that when he said that. So then getting on to the issue at hand, which is going through the maximum modulus, the way the maximum modulus principle is discussed in all these books. So I'm going to go back to page 9. And so in all these books, there's really two ways where you can find it. You can find the maximum modulus principle explained for harmonic functions, or you can find it explained for complex functions in general. Like Nehari said, they're one and the same. And in the case of Nehari, and of course I had to keep the tripod at least once, he does it in both places. So in this particular place, the maximum modulus principle is here within the context of harmonic functions. So if the function is harmonic in a domain, it cannot attain its absolute maximum or minimum at an interior point of D unless it reduces to a constant, right? So all these arguments that are done for these proofs are all about showing that the function is constant throughout the interior of the domain. And he does a proof that I didn't really understand. So then, but he also goes into page 119, the same thing, but he does it in a section which I haven't read by now. I haven't gotten that far, which he does it for general functions. But I'm going to go through it and talk about how it's done in other books as well. So then we go to Saff and Snider. And in Saff and Snider, I really like the way Saff and Snider laid it out from a physics, if you will, perspective, a real engineering perspective. And I still think, of course, that there's a missing chapter in this book that ties it all together. But I really like that Saff and Snider gives us a physical interpretation of what the maximum modulus principle is all about, which is if you had a hot plate and you're putting temperature on the borders of the plate, there may be some maximum or minimum, there may be some highs and lows in the plate as you're heating it, but when you let the system go back to equilibrium, it's going to be constant. All right, that's just the way it is. There's no free energy. And also there's arguments that are done for maximum modulus where it's basically there's zero net flux, if you guys know what flux is in vector analysis. So that is Saff and Snider. Then Saff and Snider in 165 goes through and also talks about the maximum modulus principle. Now in this case, he's doing it for regular functions. And so it's right here. And he goes through a proof of it. Very nice proof of it. Then also in page 170, he talks about it within the context of harmonic functions. I think it's theorem 26 right here. Right, so that's Saff and Snider. Again, I wish he tied it all together, but it's all in there. Then in the case of Ahlfors, Ahlfors has what I think is the best description of the problem, and he does it in multiple ways. Right down here, page 133, he's got the maximum principle. And Ahlfors does it in 3 different ways. Lays it out as the principle itself, then very quickly, almost like a topological proof. It's got a little bit of a, well, actually, it's more like a conformal mapping proof, and then goes into if f of c is defined and continuous on a closed bounded set E and analytic on the interior of E, then the maximum of the modulus is assumed under boundary of E. So there's multiple ways to say it. And then he uses Cauchy's integral formula to prove it yet again. And these explanations are really good. And then he leads into the Schwarz lemma. Okay, so Ahlfors is brief, but also actually does more. And yeah, maybe sometime in the future I need to read this whole book, actually. Then we go to Shakarchi and Stein, which I've recently got the first 3 of the 4 volumes of this series. And of course, it's very well written, but it's, I don't know how to describe it without saying anything negative, because I think it's a great series and I plan to read them someday. But it's almost like a topics course. And so a lot of times when I go, oh, I want to see how Shakarchi and Stein did X, Y, Z, and I go, I've done this dozens of times by now, by the way. Oh, let me go look at that subject. When you go find that it's either very brief, a little chunk, or it's not there. And so Shakarchi and Stein, and I believe this is true for all 4 books, but I have only 3 of them, and I mostly look at the complex analysis one because that's where I am at right now, is they went for topics, very specific topics that they thought were really important or interesting or useful for people who want to be grad students. And so, for example, there's a lot of analytical number theory in this book. So there's a lot of things that you would do if you were in analytical number theory. There's a lot of conformal mapping in the book, which is great. So I'm pretty sure I'll be using it. And in the case of the maximum modulus principle, it's a little bit like the little first bit of Ahlfors, where it's really a conformal mapping tied into a little bit of topology proof. So yeah, that was very quick. Then of course the classic Chruchill and Brown, now Brown and Chruchill, but it's really Chruchill. It's really Churchill's book. He starts off in page 175, but yet another book like Ahlfors, where I think there has to be a time and place, a time in the future where I read this whole book. There just has to be. And I considered it being my first one, but I think Saff and Snider did better for what I needed. But it's close. It's sort of, yeah, they're really comparable. And so, yeah, so when Chruchill goes into the maximum modulus principle, he does it in a way that is the Cauchy equation, very much like the third chunk that Ahlfors had, very thorough, step by step, doing callbacks to other parts of the book. And I actually wound up reading, most of what I read is from this book for the maximum modulus principle. So he lays it up, then does it through what would be called balls in topology, and then actually has a really nice example. Fantastic, an example. So this is great to read, but there are many callbacks. This is why I've got all these little things in here, all these little markers, because there are callbacks to analytic functions, where he does a similar argument that actually eventually becomes analytic continuation. Here's the explanation of analytic continuation. Then he also does Schwarz lemma. So yeah. So when I read in Chruchill, I wound up reading like half of a couple of sections and this whole section. So I think Chruchill, if this was a contest, this was the book that I would have read and be done with this issue, just to learn about the maximum modulus principle. But then In the case of Needham, I found that he talks about it, but the issue that I continue to have with this book is that Needham rethought all of complex analysis in a very unique way, and that's wonderful. But I believe that when I sit down and read this book, I'll probably have to stop everything else that I'm doing and just read it cover to cover by itself, because it wraps everything in a completely different way. It just builds all of these arguments. So by the time Needham does maximum modulus theorem, he's explained his whole Amfeld-Twist way of looking at winding numbers. He's got a little bit of topology. He's got the argument principle. And so he does it in a way that is built up. Churchill did the same, but Churchill did it in a much simpler way where it's a lot easier to follow. And so this is the problem when you jump into a book looking for something that eventually either the book lets you move around and you get what you needed, which I got out of Churchill, or you just hop around and you're like, oh, wait a minute, I gotta stop, because before you know it, I'm reading the whole book, which I want to do, but I'm doing other things. So that's my little bit about where the maximum modulus principle is done in all these books and how it is treated.